Have you ever looked at the stars and wondered, how is it possible that symbols written on paper can describe the motion of galaxies? How can a few equations predict eclipses, electricity, atoms, even the birth of the universe? This is not just a scientific question, it is a philosophical earthquake. And today, inspired by the thinking style of Richard Feynman, we begin our journey into one of the deepest mysteries ever asked. Why does the universe obey mathematics? The strange power of symbols. Let's start simple. Imagine a falling apple. You see it drop from a tree. Nothing magical, just gravity. But centuries ago, Isaac Newton wrote an equation describing that fall. A simple formula, F equals G mempon twine twine. And that same equation doesn't just describe apples. It describes the moon orbiting Earth. It describes planets circling the sun. It describes galaxies moving through space. Pause for a moment. How can the same mathematical relationship explain both an apple and an entire solar system? Why should the universe care about symbols like G or R? Feynman loved questions like this. He didn't just accept equations, he asked. Why should nature follow mathematics at all? Is math invented or discovered? Here's the first big puzzle. Did humans invent mathematics? Or did we discover something that was already there? If math is invented, then why does it work so perfectly in describing reality? If math is discovered, then where does it exist? In the human brain, nature itself, in some deeper layer of reality? Consider this. Before humans existed, stars exploded. Before language existed, gravity pulled matter together. Before symbols existed, electrons moved in predictable patterns. So somehow, the universe was already behaving mathematically long before anyone wrote an equation. That's strange. It suggests math is not just a human language. It may be the language of reality itself, patterns everywhere. Feynman often emphasized something simple but profound. Nature behaves in pattern. When we say the universe obeys math, what we really mean is this. The universe behaves in consistent, repeatable patterns. Drop an object. It falls. Heat water. It boils at a predictable temperature. Charge particles. They repel or attract in specific ways. Mathematics is simply the most precise way we found to describe those patterns. But here's the twist. We didn't just find simple patterns. We found incredibly abstract mathematical structures that predict things we cannot even see. For example, the equations of electromagnetism predicted radio waves before they were ever detected. The mathematics came first. And later, experiments confirmed it. It's almost as if the universe is built on a hidden mathematical blueprint. The miracle of prediction. Let's talk about prediction, because this is where the mystery deepens. In physics, equations don't just describe what happens, they predict what will happen. When scientists studied the atom, they developed mathematical models. Those models predicted particles that no one had seen yet. Years later, those particles were discovered. How? Because the math demanded them. It's as if the universe must follow the logic of its own equations. That's deeply unsettling and beautiful. Feynman once described physics as discovering the rules of the game that nature is playing. But here's the strange part. The rules are written in mathematics, not poetry, not philosophy, not mythology, mathematics. Why not chaos? Let's imagine another possibility. What if the universe were chaotic, not just complicated, but fundamentally unpredictable? What if objects fell randomly? What if atoms behaved differently each time? What if gravity sometimes worked and sometimes didn't? There would be no science, no engineering, no technology, no stable structures, possibly no life. The fact that the universe is orderly enough for mathematics to describe it may be the deepest miracle of all, because if it weren't, we wouldn't be here to ask the question. The deep mystery of simplicity. Another puzzle Feynman admired was this. The fundamental laws of physics are shockingly simple. Take Einstein's equation, E equals mc Ci, a short formula that connects mass and energy, two concepts that once seemed completely separate. Or consider the elegant symmetry equations that describe quantum fields. The deeper we look into reality, the more we find compact mathematical relationships underneath enormous complexity. How can something so simple generate something so vast? How can a handful of equations create stars, oceans, consciousness, and you? This raises an almost spiritual question. Is mathematics the foundation of reality? Or is it just a tool that happens to fit extremely well? Feynman's honesty about mystery. Here's what made Richard Feynman unique. He didn't pretend to have final answers. He often said, "I think I can safely say that nobody understands quantum mechanics." He accepted that mathematics works astonishingly well, but he admitted we do not fully understand why. That humility is important. We can calculate how electrons behave with incredible precision, but why those equations exist at all, that remains mysterious. It's like discovering the code of a video game without knowing who wrote it or why it runs on mathematics in the first place. The unreasonable effectiveness of mathematics. There's a famous phrase in physics, the unreasonable effectiveness of mathematics. It captures the feeling perfectly. Mathematics should not work this well. It should be a rough approximation, a crude tool, but instead it predicts reality to absurd precision. The magnetic moment of the electron, for example, matches mathematical predictions to more than 10 decimal places. 10 decimal places. That level of agreement between abstract symbols and physical reality is almost unbelievable. It's as if the universe is not just compatible with math, it is math. Are we discovering the code of reality? Think of a computer simulation. Inside the simulation, characters move according to underlying code. If those characters became intelligent, they might eventually discover equations describing their world. From their perspective, they would say, the universe obeys mathematics. But from a higher perspective, the universe is literally written in mathematical code. Are we in a similar situation? Is mathematics the operating system of reality? Feynman never claimed that, but he loved the mystery. He loved that physics is not just about answers. It's about deeper questions. The beginning of the journey, so here we are. We've asked the question, why does the universe obey mathematics? We've seen that nature behaves in patterns. Mathematics describes those patterns precisely. The laws of physics are surprisingly simple. Equations predict unseen phenomena. And yet, we do not truly know why math works at all. This is only chapter 1. We have not yet explored quantum mechanics. We have not yet examined symmetry. We have not yet faced the strange possibility that mathematics may be more real than matter itself. But now you feel the weight of the question. The universe doesn't just contain math, it seems to run on it. And in the next chapter, we will dive deeper into quantum reality, probability, and the strange mathematical fabric that governs the smallest scales of existence. Because if mathematics truly rules the universe, then understanding math may be the closest thing we have to understanding reality itself. Why does the universe obey mathematics? Now we go deeper. Because when we look at everyday objects, apples, planets, oceans, mathematics seems natural. Motion, force, energy. These feel measurable. But when we zoom in, far beyond atoms, into the quantum world, something shocking happens. Reality stops behaving like solid objects and begins behaving like equations. This is where the thinking style of Richard Feynman becomes crucial. Feynman didn't just accept quantum mechanics. He wrestled with it. He laughed at its absurdity. And he admitted something extraordinary. I think I can safely say that nobody understands quantum mechanics. Yet, despite not understanding it, the mathematics works perfectly. That is the mystery. When particles stop being things in classical physics, objects have clear properties. A ball has a position, a car has a speed, a planet has a trajectory. But in quantum physics, particles do not behave like little balls. An electron is not simply here. Instead, it is described by a wave function, a mathematical object. The wave function doesn't tell you what the electron is doing. It tells you the probability of where it might be. Pause. At the deepest level of reality, objects are not described by solid characteristics. They are described by probability equations. And yet, those equations predict experiments with astonishing accuracy. Why should probability math describe physical reality? The double slit shock. Let's talk about one of the most famous experiments in physics. Fire electrons at a barrier with 2 slits. Place a detector screen behind it. Classically, you'd expect electrons to go through one slit or the other, like tiny bullets. But what actually happens? An interference pattern appears, the kind you'd expect from waves, even more disturbing. If you send electrons one at a time, the interference pattern still builds up. It's as if each electron goes through both slits at once. But here's the twist. The interference pattern is predicted exactly by a mathematical equation. Not intuition, not common sense. An equation the universe behaves according to the math, even when the behavior makes no visual sense. Feynman once said the double slit experiment contains the only mystery of quantum mechanics. because it shows something profound. Nature does not behave according to human logic. It behaves according to mathematical logic. Reality has a probability equation in quantum mechanics. The central equation is Schrödinger's equation, developed by Erwin Schrödinger. This equation does not describe solid particles. It describes how the wave function evolves over time. In simple terms, the equation predicts how probabilities change. And yet, those probabilities perfectly match experimental outcomes. So what is more real, the particle or the equation describing its probability? Some physicists argue something radical. The wave function is not just a calculation tool. It is the fundamental reality. Matter may not be primary, mathematics may be. Feynman's path integral swine. All paths at once. Feynman introduced a powerful way to think about quantum mechanics called the path integral formulation. Instead of a particle taking one path from point A to point B, Feynman proposed something astonishing. The particle takes every possible path. Every path contributes to the final outcome, but each path contributes a mathematical phase. When you add up all those contributions, certain paths reinforce each other and others cancel out. The final result, the path predicted by classical physics, emerges naturally, but only after adding up infinite mathematical possibilities. Think about that. The universe does not choose the best path. It calculates all paths mathematically. Reality behaves like it is solving integrals. This is not poetic language. It is literal physics. Why math before observation? Here's something even stranger. Many quantum predictions were made purely through mathematics, before experimental confirmation. For example, the existence of antimatter was predicted mathematically by Paul Dirac. Dirac's equations describing electrons produced a solution that implied a particle identical to the electron, but with opposite charge. At first, this seemed absurd, but later the positron was discovered. The equation knew before we did. How can abstract symbols predict particles that no one has ever seen? It's almost as if the universe must obey the logical structure of mathematics, even if humans don't yet understand it. The language of symmetry as physics advanced, scientists discovered something else. The deepest laws of nature are based on symmetry. Symmetry in mathematics leads directly to conservation laws in physics. This connection was formalized by Emmy Noether. Her theorem showed if the laws of physics don't change over time, suddenly energy is conserved. If the laws don't change in space-phi, momentum is conserved. If they don't change under rotation, fruity, angular momentum is conserved. So conservation laws, the most fundamental principles of physics, emerge from mathematical symmetry, not from physical objects. From mathematical invariance. That's breathtaking. The universe preserves energy not because it wants to, but because its equations have symmetry. Is the universe a mathematical structure? Now we approach dangerous territory. Some modern thinkers propose a bold idea. The universe is not described by mathematics. It is mathematics. In this view, physical reality is a manifestation of a mathematical structure. Just as a triangle exists as a mathematical object, perhaps the universe exists as a vast mathematical entity. Feynman himself didn't claim this as truth, but he appreciated something critical. The more we dig into reality, the less solid it becomes. At the bottom, we don't find tiny bricks of matter. We find equations, fields, probabilities, symmetries, mathematical relationships, the limits of understanding, and yet, even with all this, Feynman warned against overconfidence. We can calculate quantum electrodynamics to extraordinary precision, but do we understand why it works? We know how to use the equations, but why these equations and not others? Why does the universe follow Schrödinger's equation instead of some random rule? We do not know, and that ignorance is important because it reminds us. Mathematics may describe reality perfectly, but explanation is deeper than description. The silent question, so here is the quiet question forming beneath everything. Is mathematics, a human invention that happens to mirror nature, a discovery of structures that exist independently of us, or the fundamental substance of reality itself? Quantum mechanics pushes us toward the third possibility. Because at the quantum level, reality does not resemble solid object, it resembles a mathematical system evolving in time. Particles appear when equations allow them to. Energy shifts according to symmetry rules, probabilities collapse when measurements occur. Everything behaves according to mathematical necessity. A universe written in equations in classical physics Math described motion in quantum physics. Math defines existence. That is the shift, and it forces us to confront something unsettling. Maybe the reason the universe obeys mathematics is because it has no choice. Maybe mathematics is not a tool imposed on nature. Maybe mathematics is the architecture of nature. In Chapter 3, we will go even deeper. We will explore why the laws of physics are so simple, why constants like the speed of light appear universal, and whether the universe could have followed completely different mathematics. Because if math is the code of reality, we must ask one final profound question. In Chapter 1, we saw that the universe behaves in patterns, and mathematics describes those patterns with shocking precision. In Chapter 2, we descended into the quantum world, where reality itself seemed to dissolve into equations, probabilities, and symmetry. Now we face an even deeper mystery. Why these mathematical laws? Why does reality follow this set of equations and not another? This is where the spirit of Richard Feynman becomes especially powerful, because Feynman was never satisfied with because that's the rule. He wanted to know why the rule exists at all. The simplicity problem, look at the fundamental laws of physics. They are not random collections of messy formulas. They are elegant, compact, symmetrical. Consider relativity, developed by Albert Einstein. One of its central principles is breathtakingly simple. The laws of physics are the same for all observers moving at constant velocity. From that principle alone, Einstein derived the structure of space and time. Time slows down. Length contract, mass and energy become interchangeable, all from a simple symmetry assumption. Why should reality respect symmetry so deeply? Why should motion at constant speed not matter? There was no obvious reason, until mathematics revealed it must be so. Constants that shape reality. Now let's look at something even stranger. The universe contains fundamental constant, the speed of light, the gravitational constant, G-Planck's constant. These numbers are not derived from deeper principles, at least not yet. They simply are. If the speed of light were different, the structure of space-time would change. If Planck's constant were larger, quantum effects would dominate everyday life. If gravity was stronger, stars might collapse too quickly for life to evolve. These constants shape everything. But here's the haunting question. Why these numbers? Why not slightly different ones? Mathematically, countless other possibilities exist. Yet the universe chooses a specific set. Is that choice random, necessary? Inevitably. The idea of mathematical necessity, some physicists believe the laws of nature are not arbitrary. They believe they are mathematically inevitable. For example, quantum field theory, the framework describing fundamental particles, is built on principles of symmetry and consistency. If you demand certain symmetries, certain equations automatically follow. It's as if mathematics narrows the possibilities, like solving a puzzle where only one configuration works. But does that mean the universe had no alternative? Or does it mean we live in one mathematical structure among many? Could the universe have been different? Imagine a universe where space has 4 dimensions instead of 3. Time behaves differently. Gravity is repulsive instead of attractive. Mathematically, such universes are possible. Physicists can write equations describing them. So why don't we live in one of those? One answer is the anthropic principle. Only certain mathematical structures allow stable matter, stars, chemistry, and life. Perhaps countless mathematical universes exist, but only a few can support observers, and we naturally find ourselves in one of them. This idea connects to modern cosmology and multiverse theories. But even then, the question remains, why does mathematics allow such structures at all? Why is mathematical existence enough to imply physical existence? Symmetry as the architect of reality. Let's return to symmetry, because it keeps appearing. In particle physics, symmetries determine interactions, the standard model of particle physics. One of the most successful scientific theories ever built is constructed entirely from symmetry principles. It describes electromagnetic weak and strong interactions through mathematical groups. Particles are not just objects. They are excitations of fields governed by symmetry. Break a symmetry and particles gain mass. Preserve a symmetry and forces behave predictably. Reality is shaped not by solid building blocks, but by mathematical invariants. This is astonishing. It suggests that matter is secondary, structure is primary. The Feynman attitude, but here's where Feynman would slow us down. He would say, yes, the equations work, but don't fool yourself into thinking you understand why. Feynman was deeply skeptical of philosophical overreach. He believed in calculating, testing, verifying. He admired the mystery. He once described physics as peeling layers of an onion. Each layer reveals deeper simplicity, but the core, the ultimate why, remains hidden. Why does a universe follow quantum mechanics? Why is space-time four-dimensional? Why do symmetries govern forces? We do not know, and pretending otherwise would be dishonest. The possibility of ultimate law, some scientists hope for a final theory, a theory of everything, a single mathematical framework from which all constants and laws can be derived. Perhaps a deeper equation explains why gravity, quantum mechanics, and space-time exist as they do. Perhaps the constants are not arbitrary at all. Perhaps they are mathematically unavoidable. But even if we found that equation, a new question would arise: why that equation? Why does that structure exist rather than nothing? We might reach a point where explanation ends, and mathematical existence simply is. The boundary between physics and philosophy, this is where physics meets philosophy. Science can describe how the universe behaves. It can derive equations, predict outcomes, test experiments. But the question, why does mathematics describe reality at all, may lie beyond empirical science. It may be a metaphysical question. Yet it is born from scientific success. The better mathematics works, the stranger the question becomes. If math were only approximate, we wouldn't ask this. But math works with terrifying precision, and that precision demands explanation. A radical thought considered this radical possibility. Mathematics does not describe reality. Reality is one solution to a mathematical structure. Just as the number pi exists independently of the physical world, perhaps the universe exists as one consistent mathematical object. If that is true, then asking why the universe obeys math is like asking, why does a triangle obey geometry? Because it cannot do otherwise. Its existence is defined by mathematical relationships. Perhaps the universe is similar. The edge of understanding, we are now standing at the edge. We see elegant equations governing nature, symmetry shaping forces, constants defining structure, quantum probabilities forming reality, mathematical necessity limiting possibilities. And yet, the ultimate why remains unanswered. In the final chapter, we will confront the deepest implications. Is mathematics more fundamental than matter? Does consciousness emerge from equations? And what does this mean for our place in the cosmos? Because if the universe truly obeys mathematics, then understanding mathematics may be the closest we can ever come to touching the foundation of existence itself. We have arrived at the deepest edge of the question. Not just why does the universe obey mathematics, but something even more unsettling. Is the universe made of mathematics? Throughout this journey, guided by the fearless curiosity of Richard Feynman, we've uncovered something extraordinary. Classical physics is written in equations. Quantum physics reduces particles to probability waves. Symmetry determines forces. Constants define existence. Predictions emerge from abstract symbols before experiments confirm them. And now we stand before the final possibility. Maybe mathematics is not describing reality. Maybe it is reality. When matter dissolves into structure, think carefully. At first we believed matter was solid, tiny building blocks forming everything. But the deeper physics went, the more matter dissolved. Atoms became mostly empty space. Electrons became probability clouds. Particles became excitations of fields. Fields became mathematical objects defined over space-time. The stuff of reality kept evaporating. What remained? Equations, relationships, symmetries, structures. If you strip away all physical intuition, what remains at the foundation of physics is not substance, but form, and form is mathematics. The mathematical universe hypothesis. Some modern physicists have suggested a bold idea. The universe is a mathematical structure. This means the cosmos does not merely follow mathematical rules. It literally is one consistent mathematical object. Just as the Pythagorean theorem is true, regardless of whether triangles are drawn. Perhaps the universe exists because it is mathematically consistent. In this view, existence equals mathematical consistency. Anything that can exist mathematically exists physically somewhere. That's a staggering claim. It suggests that physical reality is not special. It's one realization among infinite mathematical possibilities. Feynman himself never fully endorsed this idea, but he deeply respected the mystery that led to it. Why is there something rather than nothing? Here we confront the ultimate philosophical question. Why does anything exist at all? Traditional answers involve a creator, a first cause, a cosmic event, but mathematics introduces a different angle. Mathematical truths do not require creation. The number 2 exists whether or not the universe exists. The relationship between angles in a triangle exists independent of matter. If mathematical structures exist timelessly, perhaps the universe exists because it is one such structure. Not created, not chosen, simply consistent. In that case, asking, why does the universe obey math? Becomes like asking, why does a circle obey geometry? Because its existence is defined by those relationships, consciousness in a mathematical world. Now the question turns inward. If the universe is mathematical at its foundation, what about us? Our brains are made of particles. Particles obey quantum field equations. Neurons fire according to electrochemical laws. Those laws are mathematical. Does that mean consciousness emerges from equations? Are thoughts patterns in a mathematical structure? When you feel emotion, when you imagine, when you question existence, are those processes ultimately describable in mathematics? If so, then the mind itself is not outside the system. It is part of the same mathematical reality. And the universe, through us, becomes aware of its own structure. That idea is both humbling and electrifying. The beauty problem, there's another strange detail. Physicists often speak of beauty. Equations are called elegant. Theories are praised for simplicity. Symmetries are admired for grace. Why should beauty matter in physics? Why should beautiful mathematics be more likely to describe reality? Time and again, it does. Einstein trusted mathematical elegance when building relativity. Dirac trusted beauty when predicting antimatter. Again and again, beauty guided discovery. Is that coincidence? Or is beauty a reflection of deep mathematical harmony in reality itself? If the universe is mathematical, perhaps beauty is our brain's recognition of internal consistency, perhaps elegance is truth revealed. The limits of human understanding, but now we must slow down. Because here, at the edge, humility becomes essential. Feynman repeatedly warned, the fact that mathematics works does not mean we understand why it works. We may be mistaking description for explanation. We have equations that predict reality to astonishing precision. But we do not know why those equations exist. We do not know why symmetry governs forces. We do not know why the constants have their specific values. We do not know why mathematical consistency should generate physical existence. Mystery remains. And that mystery is not weakness. It is the driving force of science. 3 final possibilities. Let's summarize where this leaves us. There are 3 major possibilities. 1, mathematics is a human tool. The universe behaves in patterns. Humans invented math to describe those patterns. Its success is surprising, but ultimately practical. 2, mathematics has discovered mathematical structures exist independently. The universe follows them because they reflect deeper truths. We uncover what was always there. 3, the universe is mathematics. Physical reality is one consistent mathematical structure. Existence equals mathematical consistency. Matter and mind are manifestations of abstract relationship. Each possibility reshapes how we see reality, and none are fully proven. The silence beneath the equations when you look at the night sky, you see stars. Physics sees nuclear fusion equations. Quantum mechanics sees wave functions. Relativity sees curvature of space-time. Mathematics sees structure, and behind all of it lies a silence. The silence of unanswered why. Why this structure? Why these laws? Why anything at all? Feynman would smile at this point, because for him, the mystery was not a failure. It was the beauty of science. He once suggested that the pleasure of finding things out, even partially, is more valuable than certainty. The final reflection, so why does the universe obey mathematics? Maybe because mathematics is the language of pattern. Maybe because symmetry demands consistency. Maybe because existence itself is a mathematical fact. Or maybe because the universe has no alternative. Whatever the answer, one thing is undeniable. Mathematics is not just a human invention scribbled on paper. It reaches into atoms. It shapes stars. It governs space-time. It predicts particles before they are seen. It binds reality together with invisible logic. And here's the most profound thought of all. When you learn mathematics, when you understand an equation, you are not merely solving symbols. You are glimpsing the architecture of existence. The universe obeys mathematics, and through understanding it, for a brief moment, so do we.